Superconducting loops, trapped ions, and neutral atoms are scaling in parallel. The hardware landscape is diversifying rapidly, but operates in a disconnected, unpredictable environment. Because these physical systems possess entirely different architectures and error mitigation strategies, vendor-run benchmarks are inherently biased. The resulting evaluations are mathematically incomparable. Without fair third-party testing, cross-platform accountability is impossible. The industry requires an objective, standardized evaluation framework to force a one-to-one comparison across all providers. Metric solves this. It is an independent, open-source pipeline that executes the exact same benchmark logic across heterogeneous cloud providers and hardware architectures through a single unified runner. The platform operates on three explicit phases: benchmark definition, execution via the runner, and data processing. Once operators upload their hardware execution results, that raw evidence is aggregated, validated, and processed into a public, machine-readable visual dataset. An open pipeline is a necessity. Without transparent provenance and unified testing, self-reported claims remain unscientific marketing. This chart shows the final output of the metric pipeline, a unified leaderboard comparing entirely disparate hardware systems against a common reference point. On the far right is the metric score, a composite index aggregating total device performance across the entire benchmarking suite. The data reveals stark hardware differences. An IBM device like the Boston processor scores near 338, the Quantinuum H22 sits at 181, and a Rigetti architecture drops down to a single digit. The metric score is a scale-aware composite index, integrating multiple heterogeneous variables to reflect complex device performance. To understand what a score of 135.51 actually means, we have to reverse engineer the specific hardware diagnostics that construct it. The metric runner prevents silent configuration drift by forcing all inputs through strict JSON parameter schemas. This code guarantees that an IBM superconducting processor and an IQM processor are executing the exact same mathematical constraints at runtime. This strict standardization allows us to extract the first foundational pillar of the metric score, BESEQ, or Bell State Effective Qubits. BESEQ evaluates device-wide entanglement quality by testing for violations of the CHSH inequality across a processor's specific connectivity graph. The benchmark algorithm analyzes the coupling map and partitions it using an optimal edge coloring technique. Edges assigned the same color represent independent qubit pairs. This means they can be measured for entanglement simultaneously without any interference. These parallel tests generate two key metrics: the largest connected component size, the highest number of continuous, highly entangled qubits, and the connection fraction, which measures the uniformity of that entanglement across the chip. When calculating the benchmark subscore, Equation 12 assigns a 7/8 weight to the absolute component size and only a 1/8 weight to the device uniformity fraction. The mathematics enforce a practical reality. Total physical qubit count is irrelevant if the largest continuous block capable of high-fidelity entanglement is small. The second pillar of the metric score tracks localized defect rates using a benchmark called EPLG, or error per layered gate. Older benchmarks test all-to-all circuitry, which introduces heavy routing overhead. EPLG specifically extracts error rates along connected 1D chains, testing native entangling operations to reflect true architectural constraints. Because layer fidelity is a mathematical product of the active and idle sublayers, the total fidelity decays exponentially as the chain length increases due to cumulative crosstalk and noise. This chart maps layer fidelity against chain length. On short chains, most hardware architectures easily maintain layer fidelities above 80%, but as the chains grow, the data exposes precipitous drops on specific devices, notably IBM Fez and IBM Kingston. The benchmark isolated the physical defect causing this drop. On the Fez processor, exactly one qubit pair, indices 71 and 72, had a massive 2-qubit gate error exceeding 20%. Because layer fidelity calculates the product of all links in the chain, a single weak physical link dominates the entire mathematical calculation. In these large systems, failure is often binary. A single weak physical component creates an immediate bottleneck for the entire architecture. We have dimensionless entanglement scores from BESEQ, and localized gate error rates from EPLG. How do we mathematically combine these disparate metrics into a single logical number? The aggregation engine resolves this using explicit, scale-aware benchmark weighting. The system calculates the effective width by averaging the circuit scales a specific benchmark is tested against. A benchmark successfully evaluated across 10, 20, 50, and 100 qubits generates a large effective width. Conversely, a static, single-width test evaluated only at 10 qubits yields a dramatically lower mathematical weight. The system explicitly prioritizes and rewards device performance in larger width regimes, where error accumulation is high and classical simulation breaks down. The formula mathematically punishes processors that only perform well on small, easily simulated toy problems. It enforces accountability at scale. We return to the final cross-platform leaderboard. The system uses baseline normalization, setting one device, the IBM Torino, as the standard of 100 to convert all raw metrics into comparable ratios. The final metric score calculates a linear, convex combination of these weighted subscores. Because this aggregation uses explicit weighting instead of opaque models, every architectural trade-off is mathematically exposed. True, sustained hardware scaling requires rigorous, version-controlled datasets to accurately track progress and completely filter out vendor marketing noise. In the new era of practical quantum utility, transparent, cross-platform accountability is the absolute standard.